Looking now at how to decide how big of a sample we should be taking, if we think about why is it even important whether we know how big of a sample we should take, why not just go and take a sample of 5,000 items and that should be good enough? If we take a sample size that is too big, so we go and sample 5,000 items when we only needed to sample 500, well, we're just throwing money away. Right? Sampling takes time, it takes money. So we're wasting our resources if that's the case. On the other hand, if we go and take a sample that's too small, well, what's the problem with that? Well, now we're not going to have accurate conclusions. Small samples can lead to mistakes. Taking too small of a sample, you might make a decision based on that sample when it really doesn't accurately portray what's going on in the population. So it is very important that we do narrow it down and we get the sample of an appropriate size. So let's take a look at the steps of how we would figure out how big those samples should be. So it's going to come down to three things. It's going to come down to how confident we want to be in our decision. Now the most common we'll see is 95%, 99%, sometimes 90%. Number two, how big is the acceptable margin of error? That margin of error is also based on that confidence interval. Number three, how varied is the population? That variability, and remember, standard deviation is the measure of variability which we most prefer. That variability will not always be known to us, but it is something that we will have to either know or be able to estimate in order to decide how big our sample should be. So, if we do have to estimate that standard deviation, we can do it in a few ways. One, has there been a study run by somebody else that's looking at items within this same population of study? If there is, we can take that data and then calculate the standard deviation from that sample. Two, if all we have to work on is an estimate for the high value in the population and the low value in the population, we can base a standard deviation calculation on the range. And what we would do is take the range divided by 4. So again, we only do this if all we have is an estimate for the high and the low. So maximum minus the minimum divided by 4 will give us an estimate for the standard deviation. 3, we can go and conduct a small pilot study. So instead of taking our very broad scale study first, we go and collect data from a very small group, use the standard deviation within that small group to decide on how big of a sample should actually be taken. One of those 3 methods will have to be used in order to obtain the standard deviation if we don't have it. So if we do have an old study, we can use that. If all we have is the maximum and minimum values as an estimate, we can use that. Or we can ourselves go and run a very small pilot study. To figure out the formula for our sample size, it really comes from the formula to estimate the population mean, our confidence interval formula. If we're looking at that formula, if we look at this formula, there is actually one adjustment we're going to have to make. We are going to use the bits and pieces of this formula and rearrange them to solve for our sample size formula. But if we think about it, one of the values in this formula will actually not work for us. And that value is the t-score. Why would a t-score not work if we're trying to devise a formula that solves for the sample size? Remember that when calculating a t-score, you need something known as the degrees of freedom. Well, the degrees of freedom are based on your sample size. Your degrees of freedom are your sample size minus 1. So there's no way we could possibly go and find a t-score if we don't have a sample size to begin with. So what we're going to have to do first is, even though we should be using a t in this formula, we can't do it. So we're going to have to backtrack and go back to a z-score. And if we think about what the bits and pieces of this formula are, we have the population mean and the sample mean. And specifically, we have that the population mean is equal to the sample mean, plus or minus. Everything after that plus or minus, remember, is our error. And it's really that part of the formula that we want to concentrate on. So if we say that our error is equal to everything after that plus or minus sign, what we need to do now is to rearrange stuff within this formula to isolate for n. So we have our error, our maximum allowable error, that will be given to us in the question. We have our sample size, and that's what we need to get on the side all by itself. So the first thing we'll do is to multiply the denominator over. We get that the error times the square root of n is equal to our z-score times s. Divide the error to the other side. And now to get rid of the square root, we would have to square both sides. And we end up with the final version of our sample size formula, that the sample size should be equal to the z-score times the sample standard deviation over the error, and the whole thing squared. The bits and pieces of that equation, as we said, n, that is the sample size. That's what we're trying to figure out. The z-score, we will find that based upon the probability of 1 minus our level of significance divided by 2. The sample standard deviation, we may need to estimate that. 3 ways we can do it. Old study, max and min divided by 4, pilot study. And E, the maximum allowable error, will be a piece of given information within the question. Here we want to set up a study to determine the average amount that city council members are paid in large cities. We want the desired error from the mean to be less than $5,000 with a 95% level of confidence. And then it is estimated that the least a city council member makes is $70,000 and the most is $150,000. What sample size should we take? So we definitely have a sample size question. It is a question about mean. It's told us that they want the error from the mean to be less than 5,000. So a sample size question for the mean, our formula is n is equal to z times s over e all squared. So what are the bits and pieces of that formula? Well, we're trying to find n. Our z-score we'll leave for a second. We'll go look that up in the table in a minute. The standard deviation, well, we have 3 methods of finding the standard deviation. For this question, all we have is an estimate for the highest someone is paid and the lowest someone is paid. So we can use our range divided by 4 option. So 150,000 minus 70,000 divided by 4. So we have an estimate for the standard deviation of $20,000. The maximum allowable error, E, was set out to be $5,000. So the last piece we need for our formula is our z-score. Remember, the value we have to look up comes from 1 minus alpha divided by 2. Or for this question, we're dealing with a 95% confidence interval. So all of the confidence interval plus the error in the bottom tail, which would be half of the 5% level of significance. So we should be looking at 0.975. Or 1 minus alpha divided by 2 will tell us the same thing. Looking at 0.975, we get a z-score of 1.96. So if we take that value back to the question, we now have everything we need in order to solve for n. So simply at this point, plugging everything into the formula and solving for n, we get that n is equal to 61.46 and all the other decimals that come from that. Well, it doesn't matter what we're sampling, whether we're sampling people or cans or bolts or anything. You cannot sample a fraction of something. So the only thing we can do here is either sample 61 items or 62 items, or specifically people for this question. Well, if we sample 61 items, the formula is telling us that we're not sampling quite enough. So we always want to make sure we err on the high side. And anytime we're solving for sample size, no matter what the decimal is, we will always round up to the next integer. So what we'll say here is that we should take a sample of 62 city council members. Doing this question in Excel as opposed to by hand, the only difference is really going to be where we're getting our z-score from. We won't be using the standard normal tables, we'll be using an Excel formula, but solving for the sample size itself will really be based on the exact same formula we use by hand. So that formula is the values we need in order to solve for n are z, s, and e. Remember that the z-score is based upon the level of confidence and the level of significance. So if we have a 95% level of confidence, we have a 5% level of significance. And again, we're not looking for a probability, so not using a function involving dist, but we're doing the opposite. We're using the probabilities we have to find an observation. So when that's the case, we're using one of the inverse functions. And again, the only thing we have to find that z-score is the probability, so we should be using the function norm.s.inv, in which case our only input is probability. Remember that probability comes from all of the level of confidence plus the bottom half of the level of significance. So 95% plus 2.5% tells us we should be looking for a probability of 97.5%. or 0.975. With only having an estimate for the high value and the low value, to estimate our standard deviation, we'll have to use the range divided by 4. So it is equal to 150,000 minus 70,000 divided by 4. We get a standard deviation of $20,000. The maximum allowable error set out within this experiment was $5,000. And now that we have all that information, we can go and calculate our sample size. So it will be equal to, and we need the whole thing squared, so please use brackets, our z-score times our standard deviation divided by the error, all of that to the exponent 2. Hit enter. And again, we cannot sample fractions of anything, so we need to round that up, and we will say that the sample size should be equal to 62. Looking at how we would deal with the sample size question for proportions, again, our sample size formula will be based upon our confidence interval formula, and we remember the pieces of that confidence interval formula. We have the population and sample proportions, but really what we want to concentrate on is everything after that plus minus. And we know that everything after that plus minus is really the amount of error that we're dealing with. So taking that bit of the formula and rearranging it to isolate for n, again we have that E is our maximum allowable error. We will be given that piece of information. We need to get the n, the sample size on the side all by itself. Well, we can't deal with anything under that square root sign because remember it's as if there's a big set of brackets around it until we get rid of the z. So first divide z to the other side. Now we can go and square both sides to get rid of our square root. So we get e over z squared is equal to p hat q hat over n. So if we multiply n to the other side, and then last step, isolating for n, we get that n is equal to p hat q hat times z over e squared. Now, much like with a mean question, we may have to estimate something, and in this case we may have to make an estimate for p hat. If we don't have any estimate given to us for p hat, then what we will use is the value that p hat is equal to 0.5. Now the reason for that is remember q hat is always based on p hat. So if we have p hat of 0.5, we also have q hat of 0.5. And if we know we're going to make an error or we're not going to be accurate, what we want to do is to make the sample as big as possible. Well, if I look at the values that I'm going to multiply together for p hat and q hat, 0.5 times 0.5 is the biggest that can possibly be. If I take 0.1 for p hat times 0.9 for q hat, that would give me a value of 0.09. And if we keep checking values that we could plug in for p hat and q hat, what you'll see is that they'll keep getting bigger. So as our p hat value increases from 0.1, 0.2, 0.3, 0.4, so will the value of p hat times q hat until we get to 0.5 times 0.5. Then once we get past 0.5, what we're going to end up with is p hat's going to keep increasing, q hat's going to keep decreasing, and those two values multiplied together will start to decrease again. So the biggest number we can possibly get out of p hat times q hat is making them both equal to 0.5. And that's the reason if we have no estimate for one of them, we make them both 0.5, which will in turn make this sample as big as possible. So looking at another example, here we're going to set up a study to determine the proportion of cities with private refuse collection. We want a desired estimate within 10% of the population proportion with a confidence level of 90%. We have no estimate for what the population proportion might be. What size sample do we need to go and take? So again, definitely a sample size question. Definitely a question about proportion. So our sample size formula dealing with proportions is n equals p hat times q hat times z over e squared. Looking for all the bits and pieces of that. We're trying to solve for n. Z we'll get in a minute from our standard normal table. P hat, it tells us we have no estimate available for p hat. So when we have no estimate for p hat, what do? We try to make p hat times q hat as big as possible. The only way to do that is to make them both 0.5. Again, the maximum allowable error will always be something that is set out for us within the question. And here, it's told us that we want to be within 10% of the population proportion. So our maximum allowable error is 10%, or 0.1. So the only thing we need now is our z-score, going to our standard normal table. And what probability should we be looking up? Well, we have a 90% level of confidence. So we look up the value associated with all of the level of confidence, plus the bottom half of the level of significance. So 90 plus an extra 5% tells us we're looking up a probability of 0.95. Similarly, using 1 minus alpha divided by 2 would give us the same result. And if we look up 0.95, we find that it is sandwiched between a z-score of 1.64 and 1.65. So what we would do by hand is to take the value exactly in between there. Not 1.64, not 1.65, but 1.645. So with our z-score of 1.645, we have everything we need for our equation. 0.5 times 0.5 times 1.645 over 0.1 squared. We end up with 67.65 and whatever other decimals are after that. And as with all sample size questions, we will always round up to the nearest integer. So we would say that for this question, we are going to need to sample 68 different cities. So again, what we'll do here is quickly go through the same question that we did by hand, simply using the Excel functions instead of the standard normal tables. So ask what sample size is required. We are definitely doing a sample size question. It is a sample size question about proportion. So first, using the appropriate formula, we have the sample size is equal to p hat times q hat times z over e squared. So searching for all the pieces of that puzzle, p hat, q hat, z, and e. So it's told us that there is no estimate for the population proportion. And remember, when that is the case, we're going to have to make our sample size as large as possible. The only way to do that is to make both p hat and q hat 0.5. So if p hat is 0.5, q hat 1 minus 0.5 is also 0.5. Our z-score will come from the function norm S inverse, and it is related to something to do with the level of significance. So if we have a 90% confidence level, then we have a 10% level of significance. So looking for all the probability that would be contained below the top value of our confidence interval. Well, below that would be all the probability from our confidence level of 90% plus the bottom half of our level of significance, an extra 5%. So into the function norm S inverse, we are going to use a probability of 95% or 0.95. As always, the error will be something that is dictated to us in the question. So it says that we want to be within 10% of the population proportion. So our error is 10% or 0.1. And now that we have all the pieces of the equation, we can go and solve for the sample size. So our sample size should be equal to p hat times q hat times, and then we need to make sure that we're only squaring that piece of the formula, that is your z-score, over the error. So we are going to need to use brackets, and we always make sure that we include the multiplication sign in front of a bracket in Excel, otherwise we'll get an error. So inside the bracket, z-score divided by the error, all of that squared, and if we hit enter, we get that we should have a sample size of 67.63. We know that we can't sample fractions of things, so we're going to bump that sample size up to the nearest integer, and we'll say that we require a sample size of a minimum of 68 cities.